Glad to be with you all. We're going to present in about 40 minutes as some work we did back in 2020, fall of 2020. The title of the talk is A Field Study of Maximum Wave Height, Total Wave Energy, Maximum Wave Power produced by 4 recreational boats on a freshwater lake. And there's a long author list here. We have a larger team here at the St. Anthony Falls Lab, and Andy and I are happy to be with you today. To start off, I thought I would just orient us to where we are. So you're all familiar now with the Great Lakes region in Minnesota, but we're located right in the Twin Cities of Minneapolis and St. Paul. And we actually are on the Mississippi River, located at the St. Anthony Falls Laboratory. This is what was a natural waterfall. It was a 45-foot drop in the river. And in 1938, the university completed the construction of a hydraulics laboratory, which I assume you can see my mouse I'm circling it here. It's on the bank of the Mississippi River, built to be a hydraulic laboratory where we take water in an intake house. It falls through our laboratory and discharges downstream of the falls. So needless to say, our laboratory has 80 plus years of hydraulic research that spans hydraulic structures, energy, stormwater, river restoration, and other topics. So it's a really fun place to work. And this project fits really well within the kinds of things we do. I'm going to start with a bit of motivation on our project. So first off, the St. Anthony Falls Lab, the group that I manage, is an applied research and engineering team. We have about a 10-person research team of scientists and engineers, and we focus on local water issues that impact our citizens and our water resources. And we're working within a University of Minnesota laboratory that has a lot of faculty and graduate students, but our core mission is really the applied extent of this type of research. And I've been in this position for 20 some years now, or at least at the laboratory. And about in the early 2019, my phone started to ring quite a bit and continued into last year. It continues even today with emails and phone calls from citizens concerned about a new type of boating and the impacts they're seeing from these large recreational boats, and a need for research on these impacts. Specifically, the calls are about wake surf boats and the sport of wake surfing. The kinds of things that we heard about in our phone calls, I summarize here: adverse environmental impacts, so decrease in water quality and clarity. There's signs of erosion. People will see floating vegetation after a weekend of boating activities. We hear a lot about property damage, the impact of waves on shorelines, the impact on docks, the impact on natural elements along the shoreline like loon nests and other habitat areas. We hear about safety, impacts to smaller vessels, paddlers, swimmers, people out fishing that are getting rocked and rolled in their boats by really large waves that didn't used to be there. And then perhaps the top of the list is really what we call shared use of the lakes. We hear a lot of people that, if you boil down what their concerns are, it's that they can no longer use the lake in the same way that they were before. When these large boats come out and the large waves start, they essentially can't function anymore. They don't feel comfortable. They can't do what they came out to do, and they head back home. And so they end their activities. And so what to do about that? Our response was, this is exactly the kind of work we do in our group. We have an important role to play. And what a university can offer is we're a source, we can be a source of reliable information. We strive to be unbiased in our work. We strive to put together high quality research methods and data analysis and publications. And we can make our results accessible to different types of audiences. The last point here, remaining neutral. This is a topic that is, I could say, controversial or of high interest to a lot of different stakeholders. But our role here is we are data generators. Our role is to really do good work, do good science, and publish it. And we're trying to not get involved in setting policy and law. That's not our role here. So we did conduct a study. Our first phase was really focused on a field study to measure and quantify the characteristics of the wakes produced by recreational boats, including both wake surf boats and what we term non-wake surf boats. So how big are the wakes produced by these boats? And we're not just looking at the wave height in this study. You'll see we're going to look at the energy within the wave packet or the wave train, and we're going to look at the power produced or discharged by these waves. And we're really trying to move this discussion from anecdotal observations, probably accurate observations by different stakeholders, but we want to actually put actual numbers and research on what we're seeing. We did, and our objective here is also to produce a report, which we're happy to say we've done from the field site that is from the field study that is very robust. And Andy will talk a bit about this. This report was released on February 1st of this year, and it's been really a actively sought report. Its download is over 8,000 times. The next highest download for a St. Anthony Falls report is 500. So it's been kind of wildly popular 100-page report. So with that, I'm going to turn it to Andy, who will talk about our review process.
Thanks, Jeff. Thanks, Joe, for the introduction. Yeah, so our research review process that underwent independent technical review process that was facilitated by a senior water resources engineer with Marr Engineering Company. And the reviewers are subject matter experts in naval architecture and vessel wake waves, and they are not affiliated with the University of Minnesota. And so what we did is we submitted the report to the review facilitator, and he forwarded it to 2 reviewers. The reviewers provided detailed feedback and critique, and they actually provided 200+ comments. So it took us a long time to go through and make some changes and improvements. So we responded and addressed all the comments, and we incorporated those into the final report. And then we shared our responses with the review facilitator, who then read through them and go ahead, Jeff, to the next one. And then concurred that the updated report was sufficiently, we sufficiently incorporated the reviewer feedback, and then we published it, the final version. So our study site took place in Maple Plain, Minnesota, which is about 30 minutes west of Minneapolis. And it took place at Lake Independence, which is an 832-acre lake. And the reason we chose Lake Independence is because it's a typical Minnesota recreational lake. And also, as you can see there in the picture, on the lower, I guess it would be the southeast corner of the lake, is Baker Park Reserve, and that's owned and operated by Three Rivers Park District. And that was actually really beneficial to us during the study. It has a nice boat launch, and the park allowed us to use their some of their facilities and docks during the study. And that actually really increased our efficiency. And then within the lake, the specific study, I guess, site is on the eastern shoreline there, depicted by the red box. And we chose this shoreline because a lake owner there allowed us to use their shoreline and their dock and their lift. And that shoreline is actually it's fortified with large riprap, and so we thought that would, decrease any potential impacts by the large wakes we were planning on creating for the study. And then the substrates there are primarily sand, and like I said, the shoreline is riprap. And the water depth has a gradual increase with distance from shore, and it's about 5% slope. And as you can see there in the the figure. Just a general gradual increase in water depth. So I'm going to hop into the methods now. We tested 4 different recreational boats, and the first 2 boats that I'm going to talk about are your more traditional recreational boats that we've had or that we've seen on waters for decades, and they're not specifically designed for wake surfing. So the first one here is the Larson LXI 210, and it is a stern drive boat, also known as an inboard outboard. And the engine is positioned at the stern of the boat with the drive unit protruding through the transom. And when the steering wheel is turned, the entire drive unit turns. And the boat operator can also trim the drive unit up or down to change the performance of the boat during various operating conditions. The next boat, Jeff, is the Malibu Response LX, and this boat is a direct drive inboard, and that means that the engine is housed in the center of the boat with a straight shaft propeller that protrudes through the hull. And as the propeller pushes water past the rudder, the boat direction responds in accordance with that rudder position. And that's all controlled by the steering wheel or driver of the boat. And having the engine weight in the center of the boat helps the boat transition to planing more efficiently, which is an attribute that is popular among wake surfing enthusiasts. And then the final 2 boats are both Malibu wake setters. And the one pictured there is the Malibu MXZ. And both of the wake setters are V-drive inboards, and that means that the engine is positioned at the rear of the boat. Again, it has a shaft that protrudes through the hull that is connected where a propeller is connected, and again, the rudder position is controlled by the boat operator, and that rudder position dictates the boat's travel direction. And finally, having the weight of the large engine near the stern creates greater aft trim, which creates bigger waves or wakes. And so a little bit more about the 4 different boats here. I want to focus on 3 main things, and that's in the red box here. First is the weight. The non-wake surf boats are much lighter than the wake surf boats, and they also don't have the additional ballast weight. And like I said earlier, the wake setters are, they're basically the same boat, but the MXC is larger and heavier. And for example, when the ballast tanks are full, the MXC weighs approximately 2,500 pounds more than the VLX. And both of those boats are significantly heavier than the non-wake surf boats. The second thing to note here is the hydrofoil. A hydrofoil is a wedge that's attached to the transom of the boat, and when it's lowered into the water, it provides a downward force at the stern of the boat, which creates a greater wake. And in the first picture there on the far left is the Response LX, and that is a manually deployed hydrofoil, and as you can see there, it's fixed in the down position, and this creates approximately 1,000 pounds of downward force to the rear of the boat. And then the third picture is the hydrofoil for the wake setters, and this is an automated system that has multiple settings that can make the wake highly customizable. So you could adjust the setting to make a steeper wake for, let's say, more skilled surfers. And then the third thing to note is in the red box there is the wake shaper. And a wake shaper is a paddle-like baffle that's attached to the rear quarter panel of the boat. And again, this is just below the water surface. And for the response LX, which is in the second picture there, is an aftermarket wake shaper, and that's attached by suction cups. And the last picture is the wake setters. And again, this is an automated system that it can literally just flip out with a push of a button. And the next picture that you're going to see here is what happens to the wake behind the boat when a wake shaper is actuated, or when it's deployed. It creates an asymmetric wake that is larger and smoother on one side, and that's where the surfing occurs there. So you can see on one side it's nice and smooth, and then on the opposite side it's kind of washed out. So yeah, now I'm going to hop into the different operational conditions that we tested. And so the first condition that we tested, actually, I'm going to back up a second. Something to keep in mind is that the conditions that we tested and explain in the next few slides represents general boating conditions when doing activities like skiing, wakeboarding, tubing, wake surfing. The combinations, for example, different speeds, different ballast configurations, different hydrofoil positions, are endless. So we were testing in late October, and we only had so much time to test a few scenarios before things started freezing up. It was actually kind of crazy. It was snowing one of our test days. So with that being said, condition 1A produced the largest wave or wake for non-wake surfing boats. And this was a plowing type condition where the Larsen and the response, the non-wake surfing boats they were going 10 miles per hour. The Larsen had the lower unit trimmed to about 50%. And for the response, the hydrofoil and aftermarket wake shapers were deployed. And for the wake surfing boats, it was just a typical wake surfing condition. So going 11 miles per hour, the ballast tanks were 100% full. The hydrofoil and wake shaper were both deployed. So that was condition 1A. Condition 2 is representative of tow sports like wakeboarding, tubing, and water skiing. And all boats were on plane and cruising at 20 miles per hour. For the Larsen, the lower unit was trimmed all the way down. For the response, the hydrofoil was down, but we had removed the wake wedge. And so now the wake was symmetric. And the wake setters, the hydrofoil was down. Again, we removed the wake wedge and the ballast tanks were empty. And then finally, condition 1B. And really, the only thing that changes between 1A and 1B for the response, the Malibu response, is the wake shaper on versus off. And so in 1B, the wake shaper is off. And for the wake setters, the wake surf boats, the ballast tanks were empty for 1B, whereas in 1A they were full. And so these slight differences allow us to compare the effects of the aftermarket wake shaper and the effects of the wake surf boat ballast water weight. So how do we collect data? We deployed 3 masts, and they were tripod structures constructed of steel, as you can see in the photo there. And we deployed these in water depths of less than 10 feet. And we had a diver help us level and secure the mast to the lake bottom with a lot of weight, steel plate. And these remained in place for the duration of our field component of the study. And Each mast was a slightly different height because they were deployed in slightly different water depths. However, once deployed, approximately 6 feet of center pipe emerged from the water surface. And this is where we attached data loggers and our solar panel system and GPS receivers. And you can see that in the photo there. Can you back up one, Jeff? Sorry. And then we attached pressure transducers just below the water surface on each of the masts. And as the waves passed over the sensor, the water column height and pressure at the sensor changed. And this is how we were able to identify wave heights. And then we also deployed 2 pads. And these are rectangular structures made of steel strut. And we had cables attached to the corners. And then they were joined to a single lifting point. And this allowed us to deploy and retrieve on each day of testing. And as you can see there in the picture in the center, there's an acoustic Doppler current profiler. And basically what that does is collects high resolution data on surface wave height by recording the two-way travel time of sound waves. And we deployed these, 2 of these, one in 14 feet of water and one in 22 feet of water. And then for the boat, we needed to know where the boat was at all times while creating these waves. So we installed an inertial navigation system and a global navigation satellite system, and they were mounted to the center of the boat near the stern. And these continuously measured and logged the boat's precise GPS position and the speed of the boat. And this was at a frequency of 5 times per second. And then all this data could get positional data was later imported into AutoCAD to estimate operational distances. And to eliminate any potential speed inconsistencies between the different boats, we used the real-time speed readings of this system during testing. And then, so we drive a boat, we create waves, the waves go past the pads and masts, and we need to figure out these distances. So for each condition tested 1A, 1B, and 2, the boat made 4 passes along track lines at 225 feet, 325, 425, and 625 feet from shore. And the passes were made from east to west with a shoreline on the starboard side of the boat. And the track lines, as you can see in the photo there, ran parallel to the shore, but they were approximately perpendicular to the masts and pads. And the color lines that you see there are the actual real-time boat positional data for each pass plotted into AutoCAD. And so the perpendicular distance between each pass and each mast and pad were measured, and we define that as the operational distance. And you can see it depicted there as the white lined arrows. And that example shows the 5 operational distances between the 325-foot passes and the masts and pads. And so those, for each pass along that track line, an average operational distance was calculated. And so then at the end, you end up with 20 data points, 8 for the pads, 12 for the masts for each boat and condition tested. And these are the data points that you'll see in the results figures, and you'll see Jeff talking about.
Great. Thanks, Andy. So let's move towards data itself. First, I just want to introduce what parameters we're going to back out of the data. The first is going to be wave height, and I show a figure here in the lower corner, left corner. On the definition of wave height is just that distance from the trough to the peak of the wave. The wave period is in time. and it's the time of a single wave from peak to peak or trough to trough, or in this case, the zero crossing line. And we can take that wave height for all of the data that Andy mentioned, the average wave heights, and then we can also use that to calculate, along with the period, along with wavelength information, other attributes. And the first one I'm going to show is the equation that we use for the maximum power. This, what we'll show you in our work and is in the report, is the power within the largest wave. And you can see, if you look at this equation, essentially the unit weight of water, density times gravity, and then the wave height to the power of 2. And then the period of the wave is also in this equation. So the square of wave height times the period is essentially how the functional relationship for the maximum power. What is power? Power is the rate at which energy is moving towards shoreline. The energy is discharging out of this wave away from the boat. So it's really a rate of energy movement, or an energy flux. The next parameter that we're going to calculate is the wave energy. And in our project, we use the total wake wave energy within the wave packet. So when we pass the boat by, a number of waves are generated from a single pass. And it depends on distance. That when you're close, it's something like 9 or 10 waves. When you get farther away, that the number of waves is increased. So you get 20 some waves. And we sum up the energy within all of those waves and call it the total wave energy in the packet. The expression we use to calculate this is shown here, which is, again, the unit weight of water, again, the height squared, and then times the wavelength of the wave itself. I'm not going to go through, I'll just reference the report itself if you want to look at more information on these derivations and so forth, and we're happy to talk about that after the talk or on offline. So let's look at some results. I'm going to show you the next few slides results from our measurements. I'm going to first show you maximum wave height measured. The y-axis is maximum wave heights in inches, and this is data for condition 1A. So this is all 4 boats producing the largest waves that they can generate. The red and the blue lines and data points are for the wake surf boats, the Malibu, MXC, and VLX. And the green and yellow are the non-wake surf boats. And the x-axis is the operational distance that Andy explained a few slides ago, really the distance from the boat track line to the sensor itself. And this data all collapses. You'll see that as you get, it's a nonlinear relationship. As you get farther from the boat, the height of the waves decreases pretty rapidly. But you can see that that the 2 wake surf boats do have a higher maximum wave height. The next slide I'm going to show you is for condition 2. So this is the condition where all the boats are now on plane. They're traveling at 20 miles an hour, and they're all planing on the water surface. And I show you a red line that just helps explain that the y-axis here is different. So this 18 inches maps onto this left plot about this location. So you can see that the point here is that all of the waves for all of the boats got much smaller when we're on plane. But you still see the trend that the larger boats, the heavier boats, the wake surf boats are producing larger waves even under this condition. We can go ahead and move into energy. So again, the total energy within all the waves produced, and the same kind of trend forms here. The y-axis is the wave packet energy. The units we use here is the joules, or energy per meter of crest length. So it's somewhat of a unit energy measurement, and that's the units that we're going to typically use here. We see for the wake surf boats close to the boat are up near 16,000, 12,000 joules per meter, and you can see the non-wake surf boats are quite a bit less. And again, these are all condition 1A. Everything is making the largest waves possible here. If we go to the next slide, again, now we're planing, condition 2. All boats are on plane, 20 miles an hour. The red arrow shows where this maps. The y-axes are different here. So again, the same result, that we see total energies drop overall when we're planing, but we still see those higher energies in the wake surf boats, even when they're at cruising speeds or on plane. The next set of slides is power. So this is the power, the energy flux or power within the largest wave we measured for each pass. Same kind of trend, a nonlinear decrease. That power drops off pretty quickly as you get out to 100 feet. But you still see the wake surf boats, and especially the red boat, the MXC, which is the largest of the wake surf boats, had quite a bit of power in those waves, both much higher than the non-wake surf boats. And then when we get on plane, again, everything, those power amplitudes decrease quite a bit, and the trend is still the same, with wake surf boats contributing or having more power than non-wake surf. So I'm just going to pause and say, okay, there are several ways we can compare these data. And I'm just going to reference back to our report that if you really want to dive in, we spend a lot of time on this information, and we're going to keep moving today. But the first way we can compare is just consider a single boat and how its wakes differ between planing and plowing modes, or wake surf mode, or when our non-wake surf boats are making big waves, they're transitioning to plane. And what our data shows is that all boats see a decrease in their wave heights when they're on plane, or if they're below plane and they're in that transition, they're displacing a lot of water and their waves are going to be bigger. That's just a fact of the hydrodynamics of the hulls and how boats work. So the finding here is that all boats make higher waves with greater energy and power when they're plowing or they're transitioning to plane. The difference, however, is much bigger for wake surf boats. And that's because these wake surf boats are made to create those big waves in a subplaning condition. But there's another way we can compare the boats, and we think this is a very logical thing for us to do, is to identify something we term typical usage. What's the typical usage of these boats? In our region, for all of us, we're typically, what we've seen and grown up with is that boats are used for recreation, but most of the time they're working on plane or they're cruising around the lake. What is new here is that wake surf boats are meant to operate in a condition of transition to planing. They're actually meant to displace water, which is a completely new way that boats are used. And I think that's maybe a source of why this is such a new and challenging topic. And so we use our data and we compare against these typical conditions. So wake surf boats in surfing mode, condition 1A, versus non-wake surf boats in a planing mode. And here's what those data look like. This is maximum wave height. I'm going to show you condition 2 data. You've seen this data, but now I'm laying it on top of the condition 1A. Condition 2, so I'm planing for my non-wake surf boats, and we're in a surfing mode for wake surf boats. And what you can see here is pretty clear that in terms of height, that the wake surf boats are producing substantially higher, 2 to 3 times greater heights for the wake surf boats than the non-wake surf boats. Okay, we can do the same kind of comparison for power and energy. Here's the total wave energy in the packets for those two boats. Interesting that the non-wake surf boats, when you compare these data, you can't really see the variability here, but really around 1,000 joules per meter for the non-wake surf boats when they're planing. But the wake surf boats in surf mode, you can see that comparison in energy, 3 to 9 times greater energy measured within these with these wake surf boats. And similar true with power. This is a plot of the power under the same scenarios, comparing condition 2 and 1 for those two boats. And again, you can see max wave power, joules per meter per second for non-wake surf boats hovers around 35 to 40. And we're 6 to 12 times more power, more energy flux towards shoreline for the wake surf boats. So what do we do with that? we wanted to, again, we started out this talk by saying we're not here to make policy and rules. Every region is different. Every lake owners are different, but we can show how our data can be used for making guidance, for providing guidance. And so we offered in the report 2 examples. I'm going to show the first one here, comparing the typical usage as a way of providing some guidance. So again, I'm going to take this same plot that we looked at for maximum height, condition 2 versus condition 1. And what we do is we start focusing on the non-wake surf boats. And we make the claim in our report that non-wake surf boats are something that our citizens are used to. Our lakes are used to them. They've been around for 70 years, 50 years, pick your number, but they've been around a long time operating water skiing and other sports. In Minnesota, our Department of Natural Resources provides a recommendation for distance setback, an operational distance of 200 feet. So what we do in this example is adopt that 200 feet, and we adopt the data for the non-wake surf boats to determine a reference condition, a reference height. And in this case, it's around 6 inches of wave height that is a reference. And then we use our data to say where, at what point, what distance do our wake surf wave heights decrease to a point that is equivalent to this 6 inches of wave height. And you can see it's a little messy, right? With our data, we have data scatter, we have regression lines that we fit to this. So it's really hard to pinpoint the exact point. So Andy and I chose to just say, you know, our best estimate, if we're putting on our management hat, we're going to take this data and say, you know, to us, it looks like 500 feet is the proper distance or greater is required for those wave heights to come down. And we do the same in these 2 plots for total wave energy and wave power. Again, using the Minnesota's 200-foot setback. Again, using non-wake surf boats to establish a reference condition of about 1,000 joules per meter in total energy. And in this case, the wake surf boats need to stay better than 575 feet away. And for energy flux or power, 600 feet is the distance needed. So we just offer this as a way people can look at our information and start to think about their local situation and what's right for them. And, you know, I think it's an interesting way to look at it and provide some feedback. We do have a second example. So somebody might say, well, I don't like your typical use. How about we just look at the largest waves produced by all the boats and use that as determining the reference condition. And that's what we do in this example. Our everything is going to use condition 1A here, the largest waves we can produce, and set in the 200-foot for Minnesota. And again, what this determines, all 3 of these plots then point to 425 feet or greater is needed for those conditions to drop down to the levels of non-wake surf boats. We did a couple other studies. I'm going to go quickly through them, again, referencing the report, which is free to download. Andy mentioned condition 1B, where we compare here ballast full versus ballast empty for the wake surf boats. And these show the 2 different boats, the VLX and the MXZ. And an interesting finding that our data suggests is that we don't actually detect much difference in the ballast water on wave heights. And the same is true for power and total energy, which we don't show here. But we thought we would see a bigger difference with ballast water, without ballast water. And we really didn't see that, especially in the distances we're looking 100 to 600 feet. You'll notice that we don't have a lot of data in the first 100 feet. And that could be, we would hypothesize that we might see more difference in that region. We just didn't have the data there though. And then the other comparison is the wake shapers, the attachments on the side of the boat. This is the aftermarket one, or there's also wake shapers on the wake surf boats. Here, we're just looking at this aftermarket on or off. And what you can see is when you have that wake surf attached to your, the wake shaper attached to your boat, we had a measurable difference in wave heights, similarly with power and energy. And the conclusion here is then that there are technologies out there, aftermarket things that you can modify your non-wake surf boat into something that you can surf behind. So from a management point of view, it might mean that we need to think about not just the formal wake surf boats, but other types of boats and the ways they're being used. So that's kind of a quick skim over the work we did in the fall of 2020. Some of the conclusions here, we compared individual boats, we quantified differences in wave characteristics, and really looked at the differences between planing and non-planing activities and usages. We show that the wake surf boats produced larger waves under all conditions, and they were substantially larger under surfing conditions in condition 1A. The typical use of the boat is really important to consider, and the wave characteristics are very different between the usage modes. And I think I made the point, I think wake surfing just introduces a wholly new way of boat usage on our lakes, and that's something we need to know more about. We illustrate a method using our data to inform operational distances, and those examples suggest distances greater than 425 or greater than 500 feet are required to reduce those wave properties down to a non-wake surf boat conditions. And then we document the effects of the wake shapers as well. So that kind of wraps up our work. I wanted to just, Andy and I wanted to just put out where we're headed next. And that is the topic of propeller wash and characterization. We hear a lot of phone calls, not so much about the waves, but people worried about the wash coming off the boats, so the jet that's coming off of the propeller and projected down into the water column. Recognizing that these boats, when they're surfing, they have a higher trim angle, they're pitched up higher than planing boats, and so that prop wash is directed towards the bottom. We also recognize that these engines are really large, 400 horsepower, 600 horsepower boats, and a lot of power going into the water. And so we would like to study how deep that prop wash is projecting and how is it interacting with the substrates and with the bottom that up until now has been very quiet. It doesn't get a lot of flow and currents and velocities in these deeper parts of lakes. So this is something we're working to work on this summer. We are planning to launch a crowdfunding campaign. And if you're at all interested in knowing more, I put up our website here. We'll be announcing that campaign hopefully in the next couple of weeks. Just as a teaser, we did collect some of this data in the field in 2020, and this is some of that data, very raw data showing time along the x-axis. And these are different boat passes as the boat passed over our ADCP sensor, which was mounted on the bottom looking upward. And you can definitely see signs of a prop wash signature in the water column. And so we have yet to really look at this data. We spent all our time on what I just presented to you, but this is ready for us to look at, and we want to collect more data this summer. I think it's in many ways as important as issue as the waves impacting shorelines. So we just wanted to make you aware of that. And this last slide, I just want to thank our funders. This project was funded with a crowdfunding campaign at the University of Minnesota. We had a lot of support from our local lake associations, MinCola, Minnesota Lakes and Rivers, and Safe Wakes, a lot of other groups that help promote this. And so we're grateful for all of that support. This was fully funded by individual donations, or solely funded by individual donations, which is a pretty rare occurrence at the academic setting. Our website's listed here. And with that, Andy and I just want to say thanks, and we're happy to take questions.
Thank you, Jeff and Andy. You know, this is a really important research project that you guys did. And I know that it's, you mentioned it's been downloaded over 8,000 times, the report has, which really speaks to the influence of the work. So thank you for sinking your teeth into it and helping to provide some information on it, and for sharing that with us today. We do have some questions coming in. I will remind folks that if you have questions, please use the Q&A function. You can hover your mouse over the bottom of the screen and click that Q&A button, submit your questions that way. We'll try to get to them, and we've got about 10 minutes for questions here. So let's get to the questions. You know, one of the first questions was whether this report has been published, and I think that question was kind of asked before Andy went through the peer review process, or the review process that you guys had laid out for this project. So my understanding is that it has not been peer reviewed, published in a peer reviewed journal at this point. Do you guys have plans to submit that work to a peer reviewed journal?
I would say yes, we hope to at some point. So yeah, I'll just leave it at that.
Okay, sounds
Yeah,
good.
I mean, we want to, but as you, yeah.
Yeah, I wouldn't add, it's the realities of what it takes to get in peer review. We've went through a really long process on this one. It's 4 or 5 months to do the external, we call it, I guess, external expert review. That was very thorough by 2 authors, 200 plus comments. So it was on par with a journal peer review process. And it allowed us to be fully comprehensive in our report, which you can't get with a peer reviewed journal. You have to be quite brief. And then the other aspect is the stakeholders for this publication were citizens and lakeshore owners, boat owners. And so we didn't want this to be, we wanted it to be fully accessible. You didn't need to pay for a $2,000 subscription to an academic journal. You could just download it from our site. So those were some of the things that went in that decision.
Thanks. Yeah, I fully appreciate not putting it behind a paywall. That's a frustrating component of the research world we live in these days. Next question is, why would users want to or not want to be using ballast water while on the lake?
Well, good question. The ballast water is specific to the wake surfing boats, and it adds weight to the boat, which means it's adding to the amount of water that is displaced by the hull. So, and therefore that creates behind the boat the larger wave for people to surf upon, which is the objective of the boat. Yeah. So the ballast water just makes a heavier object, more hull exposure, and creates a bigger wave to surf on.
Do you guys have some hypotheses on why the amount of ballast water didn't really significantly change the wave dynamics? You know, that was one of your surprises that you listed toward the end there.
Yeah, excuse me. I think it has to add to the wave height. Just the physics of what's happening. I think that what we're measuring is something, a lot of our measurements were over 100 feet away. So what's going on with the waves themselves is quite complex. The waves are interacting with each other. There's actually 2 wave systems, transverse and divergent waves, that are interacting. So it's complicated what the wave heights actually are. And some of that difference when we're far from the boat might be hard for us to discern in our measurements. My hypothesis, or maybe it's not even a hypothesis, I'm wondering if it's something about the added wave height, the added energy is dissipated pretty quickly, and we don't see it once it's 100 foot plus from the boat. But it's an open question, I guess. And there is some other work that's been published, similar kinds of data that showed a similar, not a strong difference between ballasted and unballasted. And this work is published out in Portland. So I think we're not the only ones that have seen this.
Another thing to keep in mind is that non-wake surfing boats can also have aftermarket ballast bags that you throw a bag in the back of the boat and fill it up with with water with a pump, and just kind of like the wake shaper. There's aftermarket, industry selling those types of things.
Great, thanks. I'm going to keep rolling with the questions. We have a lot. Another question, just sort of on management and recommendations that could be made. Understanding that you guys were looking at really trying to provide some data from an engineering perspective on this question. Are there any technologies that could help boat operators understand how far they're operating from shoreline or other vessels? Some of your recommendations are focused around distances, and you mentioned the Minnesota regulation regulation with 200 feet. Are there ways for operators to know how far they are?
I think the answer is yes. I think it is hard when you're on a boat. I mean, right? We've all been on boats. It's hard to know what that distance is. My brain goes right to my kid who's a golfer, and he's got this fancy thing that he can shoot the distance to the pin, right? To the flag. And maybe this just has to be part of what you have on board, is you can quickly scan distance to another object until you get used to that distance. Minnesota's talking about a boater user certification where you need to be trained in and get some certification on operating larger boats, and tools to figure out these distances and be aware of your distance is part of that curriculums. There are technologies, though. Quite simply, for $50 you can get a rangefinder. $100 maybe.
Yeah. But when we're trying to understand the effects of a wave on the shoreline, is it more important to look at wave height, wave power, or wave energy?
This is a great question. It's actually still being debated in some of the things we've read. What I see out of the group, there's a research group that's quite good in Australia, that energy and power both are important. Wave height is so easy for us to measure, but really it comes down to energy and power in different ways. Nobody has come out and said, we should be using energy, or we should be using, there's still debate on which one. The difficulty is that, how do you measure energy? You'd have to measure wave height, and that's what most citizens will understand quickly. So that's how I'd answer that.
And sort of similarly, thinking about the effects of these waves on the bottomlands of a lake, there's sort of the horizontal force as the wave crashes onto the shoreline. But then there's also the scouring that occurs as the wave comes into shallower water. And did you guys look at all or think at all about the differences in the effects of the different types of crafts, wakes, on those two implications?
Yeah, this is a common question, and we did not have the time or resources to start linking the wave characteristics to environmental impact. That's our phase 2 and 3 effort, is to try and start making those measurements, and that's where we can start using a lab like St. Anthony Falls Lab, because it's, as people know, there's all different kinds of substrates, there's different kinds of shorelines and slopes. It's a very complicated topic, several PhDs probably of graduate students to answer. But how these waves interact with the bottom, what kind of shear stresses start moving different size materials, how is vegetation impacted, uprooted, breaking vegetation, all kinds of questions that we can look at. But our first step with the time we had was to just try and characterize what's out there. We know they're big waves. How big are they? And I think we took a step towards answering that.
Are you guys aware of, you guys released your report in February. You're aware of any changes in regulations or outreach efforts that have occurred using your data? Are you tracking what results have come from the policy and regulatory discussions based on your data?
Yeah, we are. I mean, we're interested. And I would say we've seen a lot of people reading. I know in Minnesota, which is where we're watching closely, they were really focused on the education, boater education piece. And so that was their priority, the priority of our legislation, our legislators. So there hasn't been a lot of, say, interest. Out in Oregon, there has been interest. We were invited to share some of our work there as they deal with some of the river systems and wake surfing. Otherwise, I think we haven't noted any changes, but I wouldn't be surprised if this gets worked in the next sessions. There certainly is a need for research like this, and other agencies and researchers ought to contribute as well. There's a real need in the country right now for this type of research.
Yeah, I think that's so right. Well, I think at this point it's 3 o'clock in my time zone anyway, 2 o'clock for many of you. And I think we've got a number of questions, 17 open questions that we're not going to be able to get to today. So I'll take this moment again to say thank you to Andy and Jeff. Really important work. I encourage folks to check out the resources that they've shared, download the report and read it further. We will be sharing this webinar, the archive link to a YouTube recording with anyone that attended or registered for the webinar. Feel free to share it with those that may not have been able to attend. And in that, we also will share their contact information. We've got Jeff and Andy's contact information here as well, if you'd like to follow up with them directly. So again, thank you, Andy and Jeff. Really great information. And we will see the rest of you at our lake conservation webinar series this fall. Take care.
Thank you so much. Thank you.
Thank you.